the way this little notation here means take the derivative of this. So here's the rule. Take the exponent, multiply it by the coefficient, and subtract 1 from the exponent. Do that to each term. This is a 1 here in front of by the x, right? 6 times 1 is 6. X to the 0 is 1, so it goes away.
That's it.
That's it.
The heck? All that work.
For polynomials, it's literally that easy. I made a video proving this for you. You don't need the proof. Noah's like, okay.
What if the second term doesn't have a variance?
So I'm going to do one of those. So what this dp dt means is derivative of, so p is my dependent variable, t is my independent. I'm giving you a little intro to this because we're going to need it later, like end of next week, beginning of the week after. But dp means derivative of p, or change in p, over change in t. What does that sound like? Change in p over change in t, or change in y over change in x. Slope, which is what the derivative gives you, correct? So the derivative of t cubed, 3t squared. Bring the 3 in front, multiply it by the 1 that's there, reduce the power by 1. I'm going to write this in another color. This is like x to the... Go to my other color, please. There we go. This is like x to the 0, so that's like plus 0 times 16 x to the negative 1. And I just keep subtracting over exponents. 0 times anything is 0, correct? So all constants, 16, have a derivative of 0. Still very easy, isn't it? Now we're told to find the horizontal tangent line. A horizontal tangent line is somewhere where the slope is 0, correct? Meaning the derivative equals 0. So if this is my function, I have to find the horizontal tangents. First thing I have to do is find the derivative. So you guys tell me what's the derivative of this?
4x to the power of 3. 4x. 4x.
Minus 4x. Done.
That was so easy.
Uh-huh.
Oh, it's money.
That's a minus. If it's multiplication, we're going to get to that. I mean, I would simplify it first so I wouldn't have to do what's called the product rule. And there's going to be some that we're going to do, and I need you to do the product rule way. Because I haven't introduced trig derivatives. I haven't introduced certain things. You could simplify out the ones we're going to do and do it without the product rule, but there's going to be a bunch of things coming up that you can't.
Trig derivatives?
Yeah, derivative of sine is cosine.
Oh, oh.
They're not that hard, but we're going to do things one step at a time. And so I need you to kind of do it the step way that I'm teaching it. Derivative of e to the x is e to the x.
Okay.
You're like, oh, that's the world's easiest derivative. Derivative of natural log of x is 1 over x. So there's a few of them that they're in your packet. You're just gonna go, okay, I need to take the derivative of this. You're gonna look. You'll get them memorized over time if you do them enough.
Oh, yeah.
But yeah, for a bit, you're just gonna have to look up what they are. Somebody did the definition of derivative, figured it out for you, and now you just have to use it.
Well, we should have a
So how would I solve this for where it equals 0?
little- I don't know. What?
How would I solve this for where it equals 0 to find my x coordinates of my horizontal tangents?
Yeah.
I would factor.
Good idea.
Well, is there a common factor? Do not think too hard about this. Is there a common factor between these?
Yes.
What is it? And x.
Yeah, yeah. Like, yep, yep. Story.
I can keep going on the x squared minus 1 with a difference of squares. And those solutions are 0. Don't forget the 0 for the 4x. The book shows what this looks like, but I know that this is opening up. It's a quartic opening up because it's a positive quartic, right? Horizontal tangents occur at extrema, local maxes and mins. So I have a rough sketch. I don't know with the information I have there, I didn't know that this left one would be lower than the right one.
2 minutes.
Wait, it shouldn't be. Oh, they showed a different graph. It shouldn't be. They should be the same. Okay, the graph that they're showing in the book is not. The one right next to it is not the one with that example. Anyways, so it's probably symmetric. It is opening up. I don't know. I don't know any of those y coordinates. I'd have to plug them in to get them. But I can know that there's maximums and minimums there. Eventually, we'll add some extra things and um, do actually sketch a curve by hand. The product rule. The product rule says the derivative of one quantity times another. I'm going to show you how this works. So I've got essentially the first one is going to be U.
Um,
Does that make sense for my two things? No, you got that? Okay. So f prime of x, that just means the derivative, is going to be u. I just take u as it is. V prime. So I take the derivative of x cubed plus 3, and that is 3x squared. U prime. V.
Oh, yeah, one half eight. Just,
I wanted it to be in the other color. I'm going to show you that it works because I'll FOIL that out and do the derivative too. So when I just simplify this, I get 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x, which simplifies down to 5x to the fourth plus 3x squared plus 6x. So I want you guys to practice doing it this way because you need practice with this rule to be able to make it work. I could, however, FOIL it out.
take the derivative.
Mhm.
Um, we-
That way was probably easier, but you need this rule for future ones that can't be done that way. Like, for instance, you're going to have something, I think Monday, like 5x sine x. And that's already multiplied together. I can't simplify that at all. I just have to use the product rule. The product rule is not bad once you get going on it. Once in a while, it's a pain to remember that this is a product. That's the hardest part with the product rule. It's not actually doing it. So that's products. Next comes quotients.
I count.
The quotient rule is a little bit of a pain. U over V. D hot. D low. Low squared.
There's a probably two over.
This isn't awful to prove. So
1 point.
let's do one.
Now that's nine. Oh, range.
So again, I'm going to do my two colors probably to make it easier. especially with how similar these are. So there's a little trick that I was taught for how to remember this. Now, this is in your packet. If you want to rewrite it with this notation instead of what I wrote there, it's fine. But this is called low D high. So top is high, bottom is low. Low D high minus high D low over low squared. Okay. Some people hate that. Some people like it.
That feels like extra steps. That's okay.
As long, whatever helps you remember it, as long as you can remember it, doesn't matter how. So the derivative is the bottom times derivative of top. Minus
AC, so there is the arc of hypotenuse. And then perpendicular to that is this direction, trying to find this.
2x
But I don't know how to do it.
all over x squared
So I don't.
plus 1 squared. The top does simplify. You do have to multiply these out. The two negatives are going to be a plus 2x here. Do you see what's going to cancel out already? A lot of times something will cancel out when you do this on top. You do have to simplify it. I'm not going to make you do incredible amounts of simplifying. Never multiply out the bottom. Noah, can you follow that instruction? Never multiply out the bottom.
I'll try.
You'll try. It's less work. No, no, it's like I can follow that less work. Like it's funny because people multiply it out and then you have to factor them again. Like in calculus, you do not expand out the bottom. Okay? If you expand out the bottom, you usually end up just refactoring it back to what it was. And you're like, that was dumb. Why did I do that work? I suppose. But yeah, mostly what happens is people expand it out and then miss the things they're supposed to cancel. You can ask Mr. Klein. He says the hardest part of calculus is the algebra.
Yeah, that's what this is so fun.
Hmm. You're like, this isn't that hard. Why did we learn calculus and before algebra? Mostly because you can't do the calculus without the algebra. The applications of calculus get real rough. But the most of what makes calculus hard is the algebra and the thinking skills. And that's why all these people that are becoming doctors are like, I'm never going to use this. I'm like, you're going to use the thinking skills. There's a little bit of a, if we're going to let you be a doctor, you have to prove you're smart enough because what you have to do as a doctor requires you to be smart. And this actually helps make you smarter, learning these thinking skills. Okay. It says find the equation for the line tangent to the curve when x equals 1. Well, the first thing I need to do if I'm going to get a tangent line is get the y coordinate. So I plug in 1. That's 4/2, which is 2. So there's my coordinate. Sometimes they'll give you the coordinates, sometimes they'll give you just the x. You must plug into the original function to get the y. Y prime, this is a quotient rule. Low times derivative of high.
Weird.
High
Otherwise.
times derivative of the bottom is 2 all over 2x squared. Okay, I expanded out the bottom because it was so easy. And I had x squareds on top.
Thing is.
So now I'm going to plug in 1, 3.
I have done this for number 17 on the.
Well, except that I didn't have 10 taught you this.
Oh, yeah.
They get a different answer than me. What did I do wrong? They did it a different way, which is fine. I can show you the way they did it second, but we should be able to do this by the quotient rule. Low times derivative of the top. Those are right. Y times derivative of the bottom. Oh, I know what I did wrong. That's a minus. So I get, that's still a minus. 2 minus 6 is 4 over 4. It's -4 equals -1. Equation for my tangent line. I use point slope, y minus 2 equals negative. You can put the 1 if you want, but you don't have to. You can distribute, put it in slope intercept if you want, but you don't have to. This one, I'm going to show you another technique because I can do this on this one. So because there's no plus in the denominator, I can do this. This would be an alternative to the quotient rule. It's important when using the quotient rule that you don't make the mistake that I did and forget the minus sign. So you see how I split this up. And we can get the first thing can simplify down to 1/2 x. Because I can cancel the x's and then x over 2 is 1/2 x. Just easier to take the derivative as 1/2 x. This one, I changed the x from the denominator to x to the -1. If I don't have something on top, that if I just have a constant on top, I can do that. Now I take the derivative. My power here is 1. 1 times 1/2 is 1/2. Reduce the power, just 1/2 for the first time. The second one, I do -1 times 3 over 2, -3 over 2, and reduce the power by 1. Again, keep reducing the power by 1. Don't bring it towards 0. Actually subtract 1. And I could get that same thing if I reduced this. I didn't bother reducing because I just plugged in numbers. But these two things are equivalent. Okay, higher order derivatives, second derivatives, third derivatives. You just take the derivative of the one before it. So if I have this equation, y equals x cubed minus 5x squared plus 2. I can take the derivative. 3x squared minus 10x. The second derivative we can notate like this. This is a little funky. This is the dy dx notation. It's d squared y over dx squared. There's a reason for that. I'm not sure I can explain it very well, but that's the correct notation. Probably again, just memorize it. Don't worry too much about the y, at least for now. If you have to learn the y later, learn the y when you already understand a lot of the other calculus. That makes sense? There is a point where you don't know enough of the calculus to understand the y, so you just got to memorize it, learn the calculus, and then later you could understand the y. So the second derivative, we just take the derivative of that derivative. The third derivative, and I've never seen anybody notate a third derivative in this way. Here's a little trick. Instead of writing 4 primes, you'll just do that with parentheses around it. So it's not y to the fourth, it's y parentheses fourth means the fourth derivative. Does that make sense?
Yeah.
Power rule is pretty simple.
Yeah.
The product and quotient rule take a little bit of practice, but they're not really that hard. Not compared to the definition. The chain rule you'll probably find hard, but it's still not difficult compared to the definition on those problems. It might be more difficult than a few of the definition of derivative problems you've done, but comparatively to doing those by definition, it's not hard.